Now we will talk about basis functions. So when we are talking about basis functions, is to deal with some cases like the XR problem. The XR is really, I would say, a simple case, that is coming from digital circuits, but you know that from like binary logic, and it represents the one of the simplest non-linearly separable problems. So we cannot solve this with a linear model. There are no solutions like what we saw before. The same kind of problem we saw before with 4 samples is some kind of XOR problem also. So here we see with the XOR, we have like 2 blue crosses, which are this one and that one. These are these 2 samples where the value is 0. We also have 2 red stars, which are the cases where the value is 1 here. So these are the 4 samples making our data sets in 2 dimensions. So this is an example of non-linearly separable data. So we cannot solve this with a linear model, but we can make use of a nice trick, which is called using a discriminant, a basis function for our discriminant. So the basis function is making a transformation of the space. So we are currently working in a space in d dimensions, the RD, what we call. So we are in a space of real values in d dimensions, and we will map this with our basis function in a new space of k dimensions. K is not the number of classes here. It's basically just a new space of a different dimensionality. Usually k is higher, if it's of an higher value than d. So we are mapping from a d dimensions to an higher dimensionality space. And the point is that the linear model will be applied in that space in k dimensions. So the space created by the nonlinear transformation will be the new space where we will work on the data. And as such, it's basically to say, okay, we have our x data that is processed, but we apply the phi function here, the phi ij, which is mapping the x from the input space here into one of the component of the space rk. So we have k of these functions that are making the mapping. And in that space, we are applying a linear, this is basically a linear model. So we are falling back on using a linear discriminant model, but in the new space. So many examples of basis functions. We have that one. The first one is kind of just the identity because it's doing nothing. It's just keeping this in the same space. But the other ones are example of different manipulations that we can make on that input space to project this into a new space. So these are kind of valid basis functions. If we're looking at this in 1 dimension, let's assume that we have really a simple case. This case is in 1D, non-linearly separable example. So the equivalent of XOR, but in 1D. So this is basically to say that we have this red sample, this sample from the red class, and we have these 2 samples from the blue class. A linear model in 1D means using 1 threshold. So it means like we just kind of cut it here. We say, okay, on one side, it is 1 class. On the other side, it is another class. So we can see here that it is not possible with 1 threshold to correctly classify this sample because we will split this. So red and blue, well, this one is misclassified. Likewise, we make this that way. Blue and red, well, this one is misclassified. There are no thresholds available that will allow us to correctly classify our data. In fact, we would need 2 thresholds to say, okay, when it's over that value, but less than that this one, it is class red. Elsewhere, it is class blue. But if we make use of that projection from 1D to 2D, so we are kind of mapping our x with, on the x-axis, the original x value, but on the y-axis, it is x squared. This is great because now we are in that function in 2D. We know that, in fact, our 1D function is simply being on that line here, which is corresponding to the x2. And then what we need to do is maybe to have a cut here. We just have to cut here with 1 hyperplane and saying, okay, everything on that side is blue, everything on the other side is red. And that's it. That's kind of linear separation in 2D. Give us 2 thresholds here. So basically where we are crossing the the x2 line basically with our linear functions. We can have different, we can have things like that or things like that. They will just put different thresholds on the in the 1D space, but the classification will be correct again. So this mapping for 1D, where the samples are non-linearly separable, get us in 2D with something that is linearly separable. So for the XR, for example, a simple solution for the XR will be this mapping from 2Ds to 3Ds. So we have this mapping function, we have x1 and x2. So we are preserving the variables as is, but we are adding a third one, which is the product of x1 and x2. So x1 times x2 give us like the third dimensions. And as such, we've got this space. So basically, we still have the same function, but in 3D now. And we can see, okay, it's maybe subtle, but if we put just some kind of hyperplane saying that lower this, it is for the red cross, and over this, it is for the blue, the red stars, and over this, it is for the blue cross. We are correctly classifying, so we can get, I would say, 0 error on that with a linear and an hyperplane in 3Ds, splitting the space that way. So problem solved. We now are able to deal with the XR problem with linear discriminant, but projecting this from 2D and 3D at first to be sure that we are in a space where the linear discriminant will be able to deal with the data.